most important part of this week. So that's the properties of linear mappings. So we want to understand what the mapping is doing and have a look at the matrices which give us in the standard basis the mapping on a plane, right? So that will be a mapping a plane into itself. So what is this one? This one means that we take simply, right, we take simply the plane and we copy the first coordinate, that's this one here, and we forget the other coordinates. So it's a projection. It's a projection to the plane. Right, xy maps to x. So it's not very nice, the arrows, so let me draw it nicer, right, this way. What about the second one? The second one does a slightly different thing. So it takes the second coordinate and puts it into the first coordinate, right? So it takes this vector and moves it to this vector, so that's this one. And as the second coordinate it provides 0, so it will be x, y, and it's mapped into y 0. Right? Why not? Why not? But it's a quite different mapping, right? You see, it's a very much different mapping. Because if I do the a square, so it's a projection, so a square will be the same as a. Whereas if I do b square, then I get 0. Well, let's go on. Let's move to C. So what does C do? C is something we understand best, right? So, well, it's just so A was a special case of C, but what is C? C is a very simple thing, because I simply take the vector in this direction and I scale it, and so that's the A times, and here I do it B times. Right, so it's nothing spectacular, just scaling. And I know in each of the coordinates I just rescale it. So if you imagine what it does with the plane, if the plane was from rubber, I would just, in one direction, I would extend it A times or shrink whatever A is, and in the other direction it would be B times. So that's the best understood thing, and you see that the best understood thing corresponds to a diagonal matrix. And now let's have a look at D. D is again quite different. D is just the mapping which we know very well, and that's the rotation. Rotation by 90 degrees, right? Because the first vector E1, it's just what happens with it, it's in the first column, right? So E1 goes to E2, and E2 goes to minus E1. So you see, it's the rotation by 90 degrees. And if a linear map just coincides with something we know, like the rotation, we know it's linear and it coincides on two values, then it must coincide everywhere in the plane, right? Because all the mapping is completely defined by its values on two different arguments. Right, so what's now the difference between those four things? So in particular, I mean B, C, and D. A was a special case. So in the case of C, we found a special basis, and the basis is such that, that's the C1, so that's this one. In the case of C, we found a basis where simply the matrix is diagonal, and therefore we can understand the matrix completely. Absolutely no problem. In the case of B, it's more difficult, and what we found as a basis is actually we found a basis where we have a chain of values. So E2 is mapped to E1 and E1 is mapped to 0. Yeah, that's what you see. The first column is 0, the second column is E1. This is what we call nilpotent mappings, and we shall see that this happens quite often. For example, the derivative on polynomials is just exactly of this kind. And clearly you can't find a basis in which B would be diagonal, right? Because if it was diagonal, then you would have to have two linearly independent vectors which are mapped to their multiples, which are and here you don't have any. So the only vector which is, so the only vectors which are mapped into their multiples are the multiples of E1, but then the multiple is 0 multiple, which is not what we really expect with the nice like C. But what about the mapping D? So there the situation is quite different, because there, as we may easily see, the problem is not that we can't find the basis in the proper way. The problem is that with the rotation in 90 degree, we have to extend our understanding of the plane to complex scalars, and then we shall find a basis of such kind, right? That's something which is more difficult. You see the picture of someone who is thinking quite thoroughly. And if I have a real matrix, I can still view the mapping it defines as a mapping of a complex plane into itself. Why not? And then you easily find vectors u and v which are actually mapped into their multiple. And one of them is I multiple and one of them is minus I multiple. And we can understand in a very short time, just following this video, why this happens and what's special of these kind of mappings which allow for the base where you have a diagonal matrix, but not in the reals, but in the complex scalars. Well, let's go on. So there is some explanation here, so please, if you are interested a little bit how to understand the things in the complex way, just read this part, right? Right, here we are in the general questions and general setup. Right, so what does it mean that we want a vector which is mapped by the map to its multiple? So this is a request that if I write it in any coordinates, I will have the matrix, and it means that the matrix multiplication of x minus a times the x, which I can write this way, should be 0. And this is nothing but a system of linear equations with one unknown parameter a, right? And it's a system of n equations of n variables, where n is the dimension of the vector space. So notice we are now working with mappings from V to V, so mappings on a space, and of course in that moment we would like to see a choice of basis on both sides of the mapping, the same one, right? So we are not interested in choosing the base for the target different than for the source, because if we did, then for the rotation, of course, we would find that the rotation is given by the unit matrix. It's enough to take any basis of the plane for the beginning, and then to see where we rotate the base and take this as the base at the end, right? And it will be just once on the diagonal. So remember, some weeks back we had the nice theorem that for every matrix you can find invertible matrices which, when multiplying with them from left and right, will bring the matrix into diagonal form with ones on diagonal and zeros everywhere else, and the number of the ones on the diagonal is equal to the dimension of the image. So translated into today's language of the maps, it means that for each linear mapping I can find bases on the beginning and bases at the end, such that the matrix of that mapping in those bases will be just this sort of close to unit matrix, and the number of ones on the diagonal is equal to the dimension of the image of the mapping. That's it, right? So that's easy. But we are interested in more complicated matter, and that's the understanding of properties of linear mappings on a space. So mapping plane into plane, space into space, R to 7 million to R to 7 million, right? Doesn't matter. And this is the thing we are supposed to solve then, right? So there is a system of equations with a free parameter, and we know that it's a system of n equations with n variables, and it has got a non-zero solution if and only if the rank of this matrix is less than the full one, so less than n. And I skipped one part. If you read carefully, you notice that I didn't talk about determinants in general, but we did have determinants in the plane, and I will come to determinants later whenever we need them. But the determinant of a matrix A, so A will be a matrix, n times n matrix over some scalars k, just over any ring it's possible to define, and the determinant is exactly as in the plane. You just make the sum of all over all permutations sigma from the permutations on n letters. Here will be signum of sigma, that says what's the sign of the permutation. So each transposition of two elements is giving you another -1 in computing the sign. So it's the even number of the even number of transpositions of two neighbors means it's plus. If it's odd number, it's minus. So just read through the text if you need, but determinant is simply the straightforward generalization from the plane for any dimension. And here we have then a product of A sigma 1 1 times and so on, and the last one will be A sigma n n, right? So we simply take from the j's column the sigma j element, right? And from each column we take exactly one. So that's the only way, and this is the only n linear form which is antisymmetric, and it is up to a scalar, right? So the determinant is n linear, you see it immediately, and it's antisymmetric because if we swap two columns, it will swap the sign of all the permutations, and we get the thing. So one more thing to remember, and again I will maybe come back once we need it somewhere essentially, but now I don't want to spend time with that and spend your time with that, and it's the fact that determinant A times B is always equal determinant A times determinant B. So determinant is actually a mapping from the matrices to scalars, and it's a group homomorphism. right? So the determinant is some polynomial expression which is easily computable, of course, for small matrices, and computable in some sense for big matrices, and a matrix is invertible if and only if the determinant of the matrix is an invertible scalar, which for fields of scalars means the same, that it's non-zero. So that works quite nice, and we can come back to our exposition because we can define what the eigenvalues and eigenvectors are, and we say that a scalar which allows for non-zero solution of this equation is called an eigenvalue, and the corresponding non-zero vectors, which are defined up to a constant, are called eigenvectors. And now you see that if you have got two eigenvectors associated with the same eigenvalue, then of course any linear combination of them is also an eigenvector, and so the eigenvectors associated with the same eigenvalue form a non-trivial vector space, and that's called the eigenspace associated with lambda. And so, for example, for lambda equals 0, if it is an eigenvalue, then it means that the kernel F is non-trivial, and it will be the eigenspace, right? So in our case of the matrices, so if I come here and go back, so in the case of B, so that was the B case, you see the only eigenvector, the only eigenvalue is a 0, because the matrix there, I can just write the matrix here, so it will again, so it was what was it, 0 0 0 1, right? So I instead write 0 0 minus lambda, 0 minus lambda 1 0. That's the matrix from this side, where you see where this is this matrix where I have to compute the determinant, and now computing the determinant gives us lambda square. And if I want to have it 0, you see that the only solution is lambda equals 0, and for lambda equals 0 it will have a non-trivial solution. So the non-trivial solution will be there if I just plug in the value of lambda, so I get this one, and you see immediately that the eigenvectors are those, right? So this is the eigenspace corresponding to 0, that's the kernel. So this is a straightforward and simple explanation. And now we have got the definition, we know that there are the eigenspaces, and we can also see by the very property of the determinants. Where did I have it here? If I change the coordinates, then I get a new matrix for my mapping. So on one hand, I have to transfer the coordinates, and to go back in the other side, there will be the inverse, right? So it will be the so-called conjugation. And then you see that you see in a straightforward way that the characteristic polynomial, as we call the determinant in lambda, it's always a polynomial which is of order n, where n is the dimension of the space in the variable lambda, and it's the same that as the original one, because the scalars are commutative. Yeah, the multiplication of matrices is not, so you can't cancel P inverse with P here, but you can cancel it here at the level of determinants, because also due to this formula, the determinant of the inverse is the inverse of the determinant. So that's very easy and very straightforward. So here I am at the definition, the characteristic polynomial. So it's a polynomial, and the roots of the polynomial are the eigenvalues. And now we are back at the example. You see how it, well, not the example, but if you look how it is from the formula for the determinants, you see immediately that there are coefficients, and the coefficients, because they are independent of the coordinates we have chosen, it must be some invariance of the mapping itself. So if you view mappings between two distinct vector spaces, so what we know already about the way how to normalize the matrices to get only the one with ones on the diagonal and zero elsewhere, we know that actually the only invariant is the dimensions of the kernel, dimension of the image. That's it. And if you go for mappings which are going from V to V, then suddenly there is much more geometry involved, right? Much more messages, many more messages, and each coefficient in the polynomial is something which doesn't depend on the coordinates, although written in terms of the matrices, right? And the three easy ones are, this says whether the dimension is even or odd, not very interesting. This is the trace, so-called trace, so it's you sum up only the diagonal elements of your matrix, and that's it. You forget about all the others, and that's a very important invariant. And then the determinant itself, and later we shall see that the trace is actually the infinitesimal version of the determinant, and the determinant says how much the mapping increases the volumes, and then the trace is the infinitesimal version of that. Right, somehow it's getting long, so I will stop now and deal with the rest in the next video. It will be the fourth one. Sorry for that.